Good morning. This is Dan Ambre from Full Spectrum Diagnostics on the behalf of Grace Engineered Products. This is part 2 of Introduction to Vibration Analysis. A little bit about me, my company, Full Spectrum Diagnostics. We do certification and testing and all different levels of vibration. We have all kinds of different classes. I've been doing it 30 years and there's always something new that pops up. We also have some live certification training. We do it on site at the customer site, or we do have public classes in the Midwest as well. But what we're getting into now, and based on all this virus stuff, is more of the interactive training. So a lot of webinar formats like we're about to get today, and some online classes that I already have a learning management system on my website if you're interested in something like that. So always something new. What you're seeing on the screen is the vibration fault periodic table. And by the way, I'm going to be a little redundant today because there's a lot of people that are joining the webinar that didn't make it last time. And
hey Dan, I'm sorry to interrupt. Could you hit the share screen button?
Oh, yeah, it went away. Okay, hold on. I don't see it. Hold on. Share my webcam.
Should be under sharing at the top.
Yeah.
There we go. Looks good.
Got it?
Yep.
Sorry, that's one glitch for the day. Hopefully that nothing else will happen. This is the vibration fault periodic table. This is something that was invented by Full Spectrum Diagnostics, and it's a guide and gives you structure to your analysis. And we're going to be using it today to show how it works. We did some of that on Tuesday. These will be a little different examples, but same sort of format. Our company, get to it. Our company also has a machinery analysis division. And I mentioned this on Tuesday that we do experimental modal analysis, which is looking for natural frequencies and structures in operating deflection shape, where you're trying to get operating information about your machinery and trying to diagnose its response. A big part of that is the animations that are created when you do this. So you get a good measurement mesh of your machine, and you bring it to life. You could put your cursor on any frequency of interest, anything that's out of the ordinary, and it'll show you the animated shape. And like I mentioned the other day, this is unbelievably useful. I've been in large crowds of people where I've presented vibration analysis studies and things that I've done, and you lose the room almost completely unless they're engaged with something. And this brings total engagement. Everybody in the room can look at this animation and say, yeah, there's something wrong. That looks like the coupling is misaligned. Yeah, exactly. And then they're all raising their hands trying to offer something that they can do to make the problem go away. So my little saying for this, trying to make vibration analysis visible and workable throughout our customers' management chain, such that they can be involved in their own asset management solutions, which is true. Everybody's helping. So it really makes my job easier and a lot more enjoyable. Third thing we have is we have an imaging division, something new that came out. There's a lot of high-speed video cameras out there. This is a version by Vibrant Technology, makers of MeScope, the animation software that I just showed you on the last slide. This video clip is processed with something called, it's a little different from others out there. It's a optical flow algorithm. It enhances subtle displacement, rescales the amplitudes, and now you can see things you haven't seen before. And this is a bearing housing on a fan, outboard bearing. You can see how it's moving, and this is real life. It's amplified, so obviously, but they had all kinds of problems with this thing, and they were always looking at the top where the bolted section for the bearing, and that's always been tight, and they've over tightened it and caused other problems. What they didn't do was go down and look in here. This is the foundation, and it looks like it's an accordion the way this thing's moving. Actually, it's down in this area where the grouted in base, something's loose under there. Either one of the bolts is pulled out, or there's a fracture or something in the grout line that's causing this motion. But we wouldn't have been able to diagnose it unless we had this type of visual animation. All right, introduction to vibration analysis part 2. We're going to talk about the basics of vibration analysis. So amplitude is how much vibration is present. Frequency is how often does it occur. It's a rate of occurrence, so we can pinpoint what's causing that high amplitude. And the third really useful parameter is phase, and it's a measure of directional relative motion. And we'll get into that quite a bit. Part 2, we're going to focus on amplitude, and amplitude's a severity parameter. We can trend displacement, velocity, or acceleration, and we can do any one of those. There is a preferred parameter, and we'll talk more on that. So the basic idea is understanding the energy levels and how those levels might impact the machine. And then we're going to talk a little bit about transducers, recommended severity parameters, overall vibration trending and analysis, and some statistics. I want to lead into ultrasonic data trends, and we're going to probably get into that next Tuesday. This is a secondary trending mechanism that the GRACE transducers have to offer. The first is you're going to take an overall level, you're going to trend that. They also have spectrum and waveform capability on demand, but also they're putting in one of the transducers in the triaxial is going to be a higher frequency transducer, and we can play with that, filter it, and adjust it so that we can see ultrasonic vibration. And what that is very high frequencies, and it's early indication of bearing failure. So I think next time I might mix it up a little bit and show you some ultrasonic trends and some technologies out there that might be of benefit for the GRACE product. PDM process, this is the overview that we talked about the other day. And again, I'm going to be a little redundant and walk through this real quick just so everybody's up to speed if you didn't make it on Tuesday. Little 7-step process that from finding the machine of interest to understanding the spectrum. Okay. First of all, the best thing to do is to know your machine. So the machine I have shown here is a direct driven overhung fan application. It's on isolators, and there's a machine base under that. That's not much more information, but this is a class of machinery. On the right here is the acceptance levels and alarm levels for 3, 4, 5, 6, 7 different classes of machinery, and there's like 18 different machine types involved in this. What we have is a fan or blower. There's integral shaft, direct driven, and belt driven. We have a direct driven version of that, and the icons along the bottom here will show you what all those machines kind of look like in profile. This is our fan or blower unit. It's telling me that the vibration allowable level for this machine statistically is 0.325 inches per second. So this is a velocity measurement. And we're going to talk more about velocity and displacement and acceleration in a minute. But this is the alarm level that would be set in the software system. So the machine's taking data every hour, every minute, what have you, and it's constantly comparing the data it's just accumulated to the allowable alarm level, which is this 0.325. This will change. This is just this whole acceptance and alarm criteria is statistically set, but it's across industry. Your machine's different from every other machine on here. And each machine, I might have 5 of these fans all lined together. They're all different. They're all going to have their own alarm criteria. They're all going to have different levels of vibration. The nice thing about having these real-time sensors that are bolted in place or magnet mounted in place is that they'll continuously take data, and any subtle change from the mean level is going to be recorded. And as a result, I mentioned on Tuesday, the alarm levels are the mean level plus 3 sigma. So statistically, that's 3 standard deviations above and below the mean curve for the data that it calculates. So as it goes in, the database calculates a new mean level, based on old data and the current data, and new statistical data, and your alarm curves get better and better. So this machine might start out at 0.325, but it might be down 275 by the time all the statistical analysis is done. There's really a lot of great artificial intelligence in the databases that can really make machine learning a good experience. So machine of interest is this direct coupled overhung fan. The main point is we have to define what is that alarm level so that we can start this data collection process and make it meaningful. Okay. This is acquiring the data. We acquire the data with a transducer. This is just showing a single axis accelerometer and what it looks like on the inside. The Grace transducers are a little different. They have their working element is on a chip inside the housing enclosure, and it's a MEMS transducer, mechanical electro machine anyway system, something like that. I can never remember what that means. So anyway, it's some type of transducer. It's calibrated. So this shows 100 millivolts per G. That's pretty common. Accelerometers will put out an acceleration signal. It starts out as a voltage. We turn it into acceleration by giving it this calibration factor, and it's somewhere around 100 millivolts per G. So, and it's when you get your transducer, it'll give you exactly what that number is. The accelerometer measures acceleration. Okay, there's a reason that we take data with accelerometers. It's because they're cheap and they're very useful. What we would like, we don't want acceleration parameter in our measurement. We would rather have velocity. And I take you back to the last page. All these little numbers here, these are all velocity values. Velocity is a better severity indicator. We can do that two ways. We can use a velometer, or a seismic velocity transducer, but this one's expensive. The seismic ones are mechanical and they fail, and they're not nearly as good as an accelerometer with no moving parts. So what we do instead of measuring velocity directly, we measure it with the accelerometer and we mathematically integrate it into velocity. Probably a little too much noise for most of the people out there. You don't really care about that, but that's the process. So that's why I have my green bolded accelerometer and the velocity parameter. And we'll talk more about that. Proximity probes are one of the other transducers. I believe that there's a way to pull those into the database as well if they're already installed on the machine. So data is acquired. Our preferred transducer is an accelerometer. Our preferred vibration parameter is velocity. And we have to remember vibration faults are directional. I'm showing you two transducers, one vertical and one horizontal. The unbalanced vector is sweeping by and it peaks out as it goes by the red transducer on the red curve here. And 90 degrees later, the blue one's going to peak out. So what does this mean? They're out of phase by a quarter of a revolution. Okay, so the heavy spot takes a quarter of a revolution longer to go by the blue peak. And these two directions will have different amplitudes. They can have different frequency content. They can have all kinds of differences. So if I don't measure the horizontal, the vertical, and the axial, I'm going to miss something. Thankfully, a lot of transducers now are triaxial, and that MEMS accelerometer is also triaxial. So we'll pick up all three directions simultaneously. What do we get? We get an analog waveform. This is voltage versus time until we put in that 100 millivolt per G calibration factor. What we're seeing is all the vibration in the system. So let's assume I'm taking a measurement on the bearing housing here. I'm picking up the rotation of the shaft. I'm picking up the cage frequency, which is the spacer between all the balls. It'll rotate at about 40% of shaft speed. So this might be 1800, this might be 900 RPM. The balls, they spin as well. So they have another vibration signature. So when you look at this, it's a complicated time waveform. It's the combination of those three different frequencies in there. Okay, kind of hard to pick out what's what, but we'll fix that. So shaft rotation, rolling element, train rotation, and a rotation of the rolling elements. Those are the three components of this so far. We can't take in that voltage measurement. It's analog and it's infinite. So what we do before we pull it into our data acquisition system is we have to digitize it. So we sample it, we digitize it at a really high rate so that if looking at this, it is a bunch of dots, but you wouldn't be able to see it because there's so many dots and they're so close together. But this is the way the computer can understand it. Okay, so we'll put in that millivolts per G number, we'll pull it into our data collector, we'll sample it and digitize it, and then it's ready for the real analysis, which is the fast Fourier transform. The fast Fourier transform, it's a computer method for the Fourier series, which is an infinite series. They do some tricks in the computer program that makes it quicker so that you don't have to wait for infinity. We apply this processing to complex signals, and we're assuming the complex signals are a sum of periodic events. In this case, it's very periodic, so sinusoidal, repeating patterns in there. So we have 3 different periodic effects in here, and one is the shaft, one is the cage for the bearing, and one is the ball themselves. The FFT processor defines those individual periodic events and pulls them out. So it strips them away from the complex signal. So this low level wiggle here, if you look at all the peaks, you can see a low level wiggle in the waveform. So it's buried in there somewhere. There's another peak of a different period length, and it's the repeating period, the rotational speed of the shaft. This is a higher frequency peak, which is probably the ball spin frequency. Has a shorter period, is higher frequency. Longer period, lower frequency. So basically what we've done, we've taken a time domain signal, this complex time waveform, we've converted it to the frequency domain. And the way we do that is with the Fourier transform, but this is the simplistic way to do it. The frequency in hertz is equal to 1 cycle over how many seconds it took to make that cycle. Okay, so I pick out 1 cycle, I start here, I go through a maximum, a minimum, and back to the original point again. If I know how long that was, let's say it was half a second, 1 divided by 0.5 is 2 hertz. Okay, 2 cycles per second. If I'm a CPM person, a cycles per minute type person, I can multiply it by 60 and it'd be 120 RPM basically. Okay, so hertz are the units of cycles per second, and the period is in terms of seconds. And the whole idea is to strip out these components and turn it into a frequency spectrum, which is what we're doing here. So I have the same periodic events up at the top, 3 different periods. If I use that frequency as 1 over the period, I can calculate their frequency component. F1 is this low frequency period. F2 is the green one, little higher frequency, but that's the period length. And the third one is the ball spin frequency, which is a shorter wavelength there. Okay, so I've just done the simple calculation and I have my 3 frequency. What I want to do and what's important, identify each peak's frequency. So I go in here and put my cursor on it, and it'll tell me what that frequency is. Now those will show up in the next step. Choose my parameter. It's either hertz or RPM or CPM. Usually RPM is the reserved for just the rotating speed of the shaft, but RPM and CPM are basically the same unit. Cycles per minute, revolutions per minute, same deal. Which peak is the rotating speed of the shaft? That's super important. So we go look on our bearing, our drawings, whatever we use when we design the machine, and we find out what the rotational speed is supposed to be. If I go onto the bearing or the motor nameplate, I can find that value, and it'll be close to what the actual under load speed is. But if it says 1765 RPM, it's probably, you know, a 2-pole or a 4-pole motor. The synchronous speed is 1800, but they don't ever run right at the synchronous speed. So roughly 1800 RPM, and that is what the information I need to know, because I'm going to ratio all the other peaks to that speed. So if that peak is 1760, I'm going to take this frequency and divide it by 1760 to see how these two are related. And the same thing between 1 and 2 there. How do we judge severity? We don't have any alarms on this yet. Okay, right now we probably have overall alarms on the waveform, but assuming that we're generating a spectrum, we have to have something to compare it to. The alarms define how much is too much. Okay. Frequency band alarms define where all our frequency ranges will have limits. This is a cookie cutter calculation for making this stair-step pattern. This pattern is percentages of the overall level. So I take 0.325 inches per second. That's my overall vibration that I'm trending. I can make alarms out of that, fractions of that in the frequency domain. Okay. I have to know a little bit of information. I want to know how my 1 times RPM relates to the other frequencies. And I can use my periodic table chart to help me with that. If I find out the rotating speed is 1760, that's F2. I want to find what this peak down here is. I put my cursor on it. It says 739. I divide it by running speed, and now I can see how it relates to running speed. It's 0.42 times RPM. So it's 40% of the speed of the shaft. Okay. F2 is 1760, so I know that that's the running speed, so that equates to the 1 times RPM. That's a synchronous frequency. I go out here, put my cursor on F3, it's 8025 CPM, divided by running speed, and I get 4.56. This is non-synchronous. It's not an exact harmonic. It's not 4 times running speed or 5 times running speed. It's 4.56. Okay, if I have non-synchronous peaks like this, it will be most likely a bearing defect frequency. Okay, we have 4 different bearing defect frequencies. They're all non-synchronous. So if we're looking for peaks in this range, that's likely to be what it is. But we have a way of, with the periodic table, to add a little structure and method to it so we can narrow down. Okay, speaking of which, this is the periodic table, and we went through it a little bit on Tuesday, but we're going to do a quick example. It's a different example, so even if you missed it, it'll be something new. Design of the machine, we're going to look at faults that can't apply. There's 35 different faults. Some of them can't apply because they're not part of the machine design, and there's no gearbox, there's no belt drive for this application, so those can come off the table. So I did it all at once instead of one at a time. I have an AC induction motor, so DC motor problems go away and fluting goes away. I have rolling element bearings, so there's no oil whirls from journal bearings. There's no gearbox. There's 1, 2, 3, 4 different gearbox faults. Those come off the table. There's no belt drive. There's a belt drive misalignment and a belt frequency. They come off the table. It's not a pump, it's a fan, so cavitation won't be a problem. It's not a specialty machine, so roll barring is a special modulation type fault. So I've dropped a lot of stuff off. I think I'm down to 23 different faults instead of 35. Okay, so now I can start my sorting. The first sorting mechanism we talked about last Tuesday is the frequency grouping. So we look at all the data we collected. This is positions 1, 2, 3, and 4. They're on the bearings, the 2 motor bearings, the 2 fan bearings. We're going to take data in the axial, horizontal, and vertical direction. So if I had one of the gauge transducers, I put it on here, it would tell me X, Y, and Z, or axial, horizontal, and vertical at position 1, and the same thing at all the other positions. What do I see when I lay them all out? I'm looking for alarm band faults. So we've created this little stair step based on the overall level of the machine. If there's any individual peak that crosses that line, we want to know about it, and there's something going on that we're going to have to investigate. For this machine, position 3 in the vertical direction, I have a high 1 times RPM, so turning speed of the shaft is 1760. So that's what pops up. It's a little above my alarm level. I'm going to have to take a look at that. I also have at position 4 in the vertical direction that same 1 times RPM problem, but I have a 4.56 times running speed. I have a non-synchronous frequency in there, okay? So my two different frequencies of interest are 1760 and 8025. One is synchronous, one is non-synchronous. So I'm going to split those two up. I'm going to first do the analysis on the synchronous frequency and then do the other. So frequency group, this peak at running speed is synchronous. So it's one of these 4, 8, 9, 10 different things. Okay. We're going to have a little more information. Consider the directional grouping. So this is radial down here. These are my 4 radial measurements. It's on the fan. It's at 1 times RPM and the highest peaks in the vertical direction. Okay. So I can get rid of all the yellow tiles on the table that were bent shaft, angular misalignment, cock bearings. Those don't apply anymore because those are all axial problems. So I'm down to 5 different problems. Okay, now what do? I look for the diagnostic that the little tile is telling me to do. So in the upper right-hand corner, there's a phase icon. So I have unbalance has a phase problem diagnostic. So does eccentricity, mechanical looseness type A, and angular offset. Right? The phase analysis we'll talk about a little bit. You don't really need to know how to do it at this point. More of an informational guide for you. It's structure in using the fault periodic table. So we have a phase test that applies to 4 of our faults, and we have a transient test that applies to natural frequencies. Natural frequencies are considered a synchronous fault. Actually, they're considered any type of fault. Their frequency depends only on mass and stiffness in the system, not rotational speed. So they can be anywhere in the spectrum and cause a problem. So we have to assume that that's a potential problem, do a natural frequency test, and make sure either refute it or accept it as the real problem. So we do this, we find out which fault is the problem. This one turns out to be mechanical looseness type A. It defied all the other phase rules for this. So we're down to 1 fault that fits the bill, and we can make our recommendations based on that. The other fault, you remember we had 2, we're going to walk through the same thing. So I consider the design of the machine, and we get rid of all the gearbox and belt drive and oil film bearings and DC motor problems and so forth. So we're down 35 down to, I think, 23 faults, same as before. Now we're just looking at a different frequency. It's this 8025 is, we take the 8025 divided by 1760, we get 4.56. So we know it's non-synchronous. We know it is on the fan bearing, and we know it's in the vertical direction. Okay. So frequency group, non-synchronous. Some of them we've gotten rid of already. There's a couple more we can get rid of. Pole pass frequency, it has an electrical response that isn't in our spectrum. Should be at 7200, so that one doesn't apply. Electrical line frequency, same thing. We should see some type of 2 times line frequency in there. We don't see it, so we get rid of both of those. Turbulent flow is usually subsynchronous, and it looks like a haystack, not a defined peak. Bearing natural frequency is usually a much higher frequency with sidebands, and the cage frequency is subsynchronous. Okay, so if we get rid of those, we're left with these 4 potential problems. One, like always, is the natural frequency problem. The other 3 are the outer race defect, the ball spin, and the inner race defect on the rolling element bearing in position 4 on our fan. So what do? We look at for directional type help. Look in there, nothing happened. So it looks like it's probably all a radial problem, but we still have to check out the natural frequency for sure. Okay. So we diagnostic test inside each of these icons is the test that's recommended, an ultrasonic analysis. So we pull an ultrasonic spectrum and look for impacting in the high frequency spectrum. And then we also do transient natural frequency test. So there's our diagnostics. And as it turns out in this case, we found that it was an interrace bearing defect. Okay. These three will have three specific frequencies that we'll be looking for. If we know the bearing make, model, and type vendor, we can determine what all these frequencies are. So two of them didn't pan out. This is the one that fits the mold. So it had a bearing defect and it had a mechanical looseness type A problem. So looseness in that bearing was likely what starts the jackhammer effect, and it shows up on the bearing as the bearing starts to fail. Okay. All right, now the new stuff. And if you have any questions about any of that, you might want to go over yesterday's webinar or Tuesday's webinar, because it'll give you a lot more information. You can watch it live on YouTube, recorded on YouTube. Okay. We're going to talk about time, amplitude, frequency, and phase. The key things are amplitude, frequency, and phase. Those are the biggest diagnostic tools. Amplitude is a severity indicator, so it's how much. Okay. Here inside the icon, there's mils, and there's inches per second, and there are Gs. So this is displacement in thousandths of an inch. This is inches per second. It's velocity. This is acceleration in Gs. Okay. So this is our first wave. This is how our online transducers work. They'll be collecting data and doing analysis until an alarm is exceeded. So it's our first wave that something has changed and something's impending failure. We're going to have to figure out what it is before it fails. Frequency, there's hertz, which is cycles per second. There's orders, it would be 1 times, 2 times, 3 times, 4 or 5 orders of shaft rotation. So it's just normalized frequency. And CPM and RPM are cycles per minute and revolutions per minute. Frequency is how often the fault occurred, or if we go from the time waveform to the frequency domain, it's going to show up as a peak in our spectrum. And that peak is also going to be alarm criteria, probably as an overall level and as a spectrum band alarm. We'll get a little bit more into that as we go. The last thing is phase analysis. So phase is motion and direction. It's showing us how the machine is moving. And what we're really interested in is usually across couplings. If we have a coupling misalignment in the radial direction, we'll show that radial 180 degrees out of phase response. Kind of like that first animation I showed on the second slide of this presentation. We also look across the machine for bent shafts. We look on the bearings for cocked bearings. So there's several things that we can use phase for. What makes it incredibly useful is there's about 12 different problems that all have the same frequency signature. They show an elevated 1 times RPM response. So basically everything, if you're looking at the table, everything that's a synchronous problem in the first 2 columns of the table plus natural frequencies, that can be what we're looking for. We're trying to distinguish all of those things. And phase analysis allows us to do that. We'll show you how that happens. Okay, and time waveform, that's the basic signal. That's where everything starts. And when we talk about time a little bit, it includes all the amplitude, all the frequencies, and all the phase information in one little package. Unfortunately, it's real simple to look at when you're looking at one frequency and one wiggle in the shaft, but they get awful complicated. So when we go from the time domain to the frequency domain, it's really the way vibration analysis should be done. There's only a couple of problems where we need the time waveform directly to make a diagnosis. The rest of it is in the frequency domain. The overall amplitudes, very trendable. So here we're showing horizontal, vertical, and axial. Assuming this is a triaxial transducer, they're all sampled simultaneously, and we'll have 3 different amplitude trends. If we need to do an FFT analysis, it looks for the periodic events and calculates the frequencies. Okay, so in this case, they're all rotational speed, probably an unbalanced type problem. Okay, they also have phase. Now the time waveform phase, it's a shift indicating a directional motion. To have this shift, we need two different time waveforms to compare. So if we're on the same bearing, we might go from bearing 1 to bearing 2 in the vertical direction. And if they're both moving the same way, then they'll lay on top of each other like this. So one might be higher than the other, but we have basically a 0 degrees phase shift if they're moving together. If I have a horizontal and a vertical vibration and one on the same bearing, we're looking for an unbalance effect. Remember, we did that, showed that animation, and we have the red one going past the transducer, and then a quarter of a revolution later, the blue one goes past the transducer. That's a 90-degree phase shift. So we can look directly in our time waveforms and see that shift if they're clean enough, obviously. There's other methods. We can use a laser tack and compare the heavy spot in the shaft to the laser tack location and see what that is as well. There's a couple different things we'll look at a little bit later on in the presentation. So 0 degrees, 90 degrees, this is 180 degrees. So they're moving completely out of phase. So this would be across a coupling, basically. This is a misaligned coupling because one half is moving in one direction and the other half's moving the other way. They're always fighting each other. Okay. All of these occur at 1 times RPM, or potentially can occur at 1 times RPM. So unless you had phase, you wouldn't be able to decipher the difference between them. And that's why we use it. So pretty important. Okay, we're going to talk about amplitude first. Amplitude is how much, it's severity, it's where we start off. So the first thing we're going to do when we have one of these transducers installed, and I'm just showing one direction here, so that really you're getting X, Y, and Z, and you'll get 3 trends, is just the time waveform. We'll pull that out. We have some algorithm inside the logic of the transducer that stores the highest amplitude, and that's what we see in our trends. We use this amplitude to set new alarm levels. So this might be an alarm level based on my chart of rules of thumb, 0.35 inches per second when it runs down here somewhere. I don't want to use 0.35 inches per second if I'm running at 0.1 all the time. I want to know how big and how fast it changes from 0.1 to 0.15 or 0.1 to 0.2. If I had this type of alarm on there too highly set, I might miss something like that. So that's the greatest thing about doing these transducers to stay in one place all the time, and they're constantly taking data. There's no human interaction to bother them. They get fantastic trends. This would be like January, February, March, April, all that for route-based measurements. You get 12 measurements a year. If I took a measurement every day, I'd get 365 measurements with the in-place wireless transducers. If I took it every hour, I'd have almost 8,800 measurements. Every minute, 350,000, something like that, something ridiculous like that. There is data overload, but you're going to get fantastic trends in this. You'll be able to see real subtle changes that are from plant processes instead of, just motion from month to month, taking the transducer on and off, things like that. Okay, great trends. So amplitude-wise, that's what we're doing. What can these amplitudes be? They can be displacement in mils, typically, or microns. There's velocity in inches per second and acceleration in Gs. Those are the units that we prefer, right? 3 different types of measurements. This is the one that's preferred, the velocity, and we'll tell you why in a few minutes here. All right, here's my alarm for my machine of interest, 0.325. I don't want to wait this long for this thing to creep up to failure. I want to see it right here, maybe, where something has changed and I don't know what that is. So we can pick up subtle changes, like I mentioned, with the online systems much faster. Vibration parameters themselves, we just mentioned that we can take displacement, velocity, or acceleration as our parameter of interest. Which one's best? Well, maybe we got to tell you what they do first. The displacement is usually measured with proximity probes directly on the shaft. Proximity probes are usually designed for oil film bearings where there's no rolling elements. And what they'll do, the shaft rides on an oil wedge as it rotates. So what the probes are for, they are inserted through the bearing housing, and they come really close within about 50 mils of the shaft, 30 to 50 mils. And they have a magnetic flux that changes with shaft motion. So they're able to detect thousandths of an inch, really tiny measurements, tens of thousands. And it's real detailed. You can't get that on the housing of a journal bearing. All the vibrations in the shaft, and it has to go through the oil wedge and then the bearing housing, and the housings are pretty big, and it gets muted out by the time it gets to an accelerometer on the housing. So it's really good if you have journal bearings to use displacement with your proximity probes. We use velocity pretty much. You can, for all vibration measurements on rotating equipment, you can measure it directly with a velometer or something called a seismic velocity transducer. But that isn't the easiest method. The velometers are expensive. The seismic transducers are mechanical, so they can fail. The easiest thing to do is integrate that signal mathematically from an accelerometer. So actually we're taking an acceleration measurement and we're mathematically turning it into velocity. There's very few drawbacks to doing that, except extreme low speed rotating machines. So that's the standard method. Acceleration is measured directly from an accelerometer transducer. There's a few good reasons to use acceleration, one of which is high-speed gearboxes. If you have centrifugal compressors, they have lots of teeth on their high-speed shafts, and you can get really high gear mesh frequency. And that's one of the limitations of velocity. You don't see those gear mesh frequencies nearly as well. And manufacturer usually quotes their alarm levels in acceleration. Okay, we're going to talk first about amplitude displacement. And this is a little complicated, but it makes a lot of sense once you see how it goes. And it's a real simple explanation, but there's a little story to it. Failure modes from vibration, they come in two methods. One is overload, which is low cycle fatigue, and one is repetitive loading, which is high cycle fatigue. Low cycle fatigue can usually be designed out, but there's something that's changed recently in the power industry. They're not using main coal power plants anymore as base load. They're using a lot of them as peaker plants. And you have all these really big pieces of equipment, a lot of forced draft and induced draft fans, and they're not made to start and stop. You start them, and 2 years later, you turn them off at the outage. But now they're starting and stopping every day. You get a lot of low cycle fatigue from that big torque and that change in temperature really quick. So the overload capacity, these things really shoot to a high level when you turn them on. There's no soft start. They were never designed for that. And you start to get low cycle fatigue problems. And then you have to start limiting how many times you can do that a day or a shift before you're going to cause real big problems. Repetitive loading, we get high cycle fatigue. We want to stay under that limit so that it lasts forever. And on our chart, this is called an SN chart, which is stress and cycle diagram. You can see there's a low cycle fatigue line. There's something called an endurance limit, which is where we want to be, because if we're on this side of the endurance limit and we're low enough underneath this curve, we'll have infinite life. Okay, or pretty close to that. Stress reversals on a log scale. So this is cycles and this is amplitude. We want to be under this curve. Okay, and this is cycle limited, frequency limited. This is not once you get the amplitudes below that. So there's a level of dynamic stress that can be tolerated forever, and that's beyond, underneath the endurance limit. And that's what we're rooting for here. Did a little fun exercise, and it makes a lot of sense. So what I'm trying to say is displacement amplitude is a function of frequency. And I'm going to show you that it actually is. Here's just a paper clip. Okay, we can bend it to extreme amplitudes without immediate failure. However, if we apply the loading multiple times, the clip will break after a small number of applications. This is overload or low cycle fatigue due to a dynamic loading. Okay, I take paper clip number 1, 2, 3, 4, 5, 6. I have 4 bends before it fails, 4, 5, 6, 6, 8. So an average of 5.5 cycles to fail. If I open this up 180 degrees, bring it back, open it up, bring it back, doesn't take very long to fail. Now, if I open it up to 90 degrees, I get 16, 17, 18, up to 23 cycles. So it averages 19.5 cycles before it fails. Third one, I go 45 degrees, and I even get bigger numbers of cycles. So on average, about 70 cycles to failure. So cycles or frequencies of stress reversals, 5.5, 19.5, 70. My amplitudes are going down, and the cyclic life is going up. Okay, so displacement, which that's all this is, I'm bending it, flexing it. 180 degrees, I get a limited lifetime. So I can only do that 5.5 times, and then it's going to fail. So this is my failure line, my displacement failure line. And if I'm a big fan in a power plant, and my vibe guy comes to me and says I have so many mils of vibration, I can't do anything with that. He has to tell me what frequency he's talking about, so I can gauge what that amplitude is and what it means. If I have 5 mils of vibration, that's okay here, but it's not here. I'm not going to get 70 cycles out of that. It's limited right there. Okay. The endurance limit is about 1 million cycles. So in mechanical engineering, if you design something to have a cyclic life below a certain threshold, it'll last forever, and that forever number is 10 to the 6 or 1 million cycles. So it'd be 1 million revolutions of a shaft. Okay, and the lower you go, the more cyclic life you have. Okay, I have a large induced fan in my power plant. The vibration analyst says the bearing vibration amplitude is 5 mils or 5 thousandths of an inch. Is this amplitude acceptable? Can I even answer him? I need an additional piece of information. We just learned that displacement vibration is a function of frequency. I need to know what the rotational frequency of the fan is, then I can tell him my answer. Now, part of this answer is the rotational frequency. The other part is my starting point, my velocity. Okay, my velocity in inches per second for this type of fan that we have in the power plant, 0.325 inches per second. So I need to calculate how much displacement is equal to 0.325 inches per second. If I stay under this velocity value, I'm going to have infinite life. It'll be below my endurance limit. If I go to 0.5 inches per second, I'm above my cyclic limit and it'll fail. Okay, so I want to know, is 5 mils above or below this limit in velocity? Okay, there's a way to do it with an equation. I don't expect anybody to do this, but this is the relationship that you got to start thinking in your head. The overall alarm for this class of equipment is 0.325. That's velocity. If the measured vibration is 5 mils of displacement and we have a rotational speed of 1790, we can calculate the allowable displacement. Okay, and I don't want to do this. So I would say, hey, go back and take a velocity measurement. So I don't have to do this every time. And now we can use this 0.325 inches per second. But there are cases where people do this. So we found out that there's 3.47 mils is equal to 0.325 inches per second. So this is the equal displacement for 0.325 inches per second. So the machine's not acceptable. We're running at 5 mils. We're way above this. Okay, and we're on the bad side of that allowable curve. Now, if he said we have 8 mils of vibration, I'd have to go back in with the same information and calculate what is the allowable displacement limit based on the velocity for 8 mils and find out if that's good or bad. And it's going to be bad again. Okay. Now, this is a roundabout way. I just wanted to get it through your head, this is variable. So the displacement amount isn't enough. You have to tell me what frequency we're talking about so that I know where I am along this curve and what's allowable. So that's kind of tedious. If I use velocity instead, and my velocity is 0.3 inches per second, the stress due to that velocity is going to give me infinite life. If the stress is above roughly 0.3, we'll have finite life. And I say 0.3 because if you look at all the alarm values and the acceptable curves and so forth, 0.3 is like right in the middle. So here's my criteria now. Now, why is this important? This flat part of the curve is velocity. It's an energy level. It's not related to frequency, and it's flat. So if my frequency is 1800 RPM, I have to worry about 0.3 inches per second. If my frequency is 5400 RPM, same thing. I look at just a threshold level. Okay? It makes it so much simpler. So, you know, it's easy. It's easy to do. You don't want to be calculating an allowable displacement for every number that comes through. You just go with the velocity, kinetic energy related alarm value, and it's you get great results. And they've been doing this for a long time. So I sorry about the long roundabout way of explaining this, but that's what people still don't quite get in their heads when they quote the displacement values. You have to know what frequency it is to see where you are and what amplitude you can tolerate. Okay. Now, acceleration has the same type of problem. There's an acceleration or an inertial force generated will increase with speed and will be a function of frequency. The centrifugal force, the unbalanced force, there's a mass offset and there's a radius offset of that mass, and there's RPM in here, and it's RPM squared actually. So it's even a little more nonlinear. But this is the path it follows. It opposes the displacement path that we talked about earlier. They almost meet in the middle. It's a little off, and I'll show you that in a sec, but this is the trend. So if I'm quoting things in acceleration, let's say I have 12 Gs, is that good or bad? You have to tell me what frequency we're talking about. I have to calculate an equivalent velocity level and see if that's good or bad. So it's tedious. So you really don't want to use acceleration and you don't want to use displacement unless you're, a proximity probe where you're measuring it directly. You want to use velocity. It's great over a broad range of frequencies, and it's a very simple alarm criteria. Here's what's called the contour of equal severity. This is the velocity measurement. So I have it from 2 Hertz up to 10,000 Hertz. It's pretty flat all the way across there. These are the equivalent displacement for this value of vibration. So if this is 0.3 inches per second at 10 Hertz, the equivalent displacement limit is 10 mils. Okay, the equivalent velocity limit, but at that 10 Hertz is 0.07 Gs. So 0.07 Gs doesn't mean anything to me. 10 mils doesn't mean anything to me unless I know for sure what the frequency is. It's so much easier just to use the velocity as a across the board severity limit. Okay, so reinforcing the point, this is the best alarm parameter is velocity due to its flat response and its independence of frequency. And when we're looking at amplitudes, here's something I brought up on Tuesday. I'll do a little more of this next Tuesday, but this is some sampling and some statistics on just 4 days of data from a power plant. So this was a big vertical pump. I have a bunch of statistics in here working on this, but I'm looking for an alarm criteria. And what I have is a value that's changing the more data I get. As I'm taking data, I'm adding to my statistical population. And once I get out here 4 days later, my alarms criteria has gone down here and it's squeezed in there. And by the way, I do want to have alarms in both directions. These alarms are set by a mean plus 3 sigma distribution. So the mean value, the average value, plus or minus 3 standard deviations. And that's what gives me these curves on either side. The top one, obviously I want to know if vibration goes up, I want to be able to detect that, but also I want to detect if vibration goes down. If I go from 0.175 inches per second and I drop down to 0.1, something changed, something happened. It might not be good. You know, usually low vibration is good, but maybe it's the machine turned off. It shut down for some reason. And now I'm not taking any data, it's flat. And sometimes that happens. You'll run a machine, or you'll have non-operating machine and you won't know it until something else tells you. Okay. Oh, the other thing, we can trend more than one parameter. Okay, I mentioned earlier the Grace nodes, they have a triaxial MEMS accelerometer in them. 2 of those axes, the X and Y directions, I believe the frequency range is 1,000 hertz. The third direction, they're starting to change out those and make that, I think, an 8,000 or 9,000 CPM or hertz signal. So they're going to have better capability in the transducers they currently have. They're going to be able to monitor the X, Y, and Z low frequency range. Plus, they can do some sampling and bandwidth filtering to be able to get the really high frequency usefulness out of them. So 5 kilohertz up to 8 kilohertz or whatever the limit is on these. So that's a nice development. Way to go. This is the severity chart, the amplitude parameter severity, bearing health for rolling element bearing machines. Oh man, I didn't get through nearly as much as I wanted to today. So this severity parameters, we already talked a little bit about the walkthrough. I just noticed it's almost 11 o'clock. I will try to fill in just a minute. Amplitude parameters, there's severity here. This is another suggestion. There's different frequencies that are bound to show up based on the design of the machine. So there's 1 times RPM, there's blade pass frequency, there's gear mesh frequency. You're popping up a packet of overall energy information from this chart, basically, every second, every time you collect data off your machine. And it comes up as a kilobyte package or whatever into the cloud. There is a way you can probably do that with each frequency you're interested in. So this is 1, 2, and 3 times harmonics. There's subsynchronous, there's blade pass. If you know what the bearing is, you can put those values in and upload just that tight frequency band instead of the whole spectrum. I believe the spectrum's calculated originally, and then if you just filter off different sections, you get all kinds of statistical information on discrete frequencies in the spectrum. Anyway, I got a couple more slides. Well, it probably might be too many for this. I'm gonna have to cut this off, I believe. It is 11:58 right now, my time. Are you there, Nick?
Yes, sir. You want to run through some of these questions?
Yeah, and well, before I do that, I'll run through the last few slides next time. So I'll leave where I left off here. I'm sorry I took a little longer than I expected to, but that's a good stopping point. We finished with the amplitude. We'll go into frequency and phase, and then we'll do some ultrasonic stuff on Tuesday. So it'll be good stuff.
Sounds good.
Yeah, let's do a few questions.
All right. So First question comes from Richard. When you set up the alarms for a fan or a blower, do you have a different alarm level for the motor?
No, the motor really doesn't exist anymore as far as being of interest. You will do whatever let me see if I can get back to that. There we go. Okay, on this list, you have a piece of equipment. It's whatever the motor's driving. That's what you set the alarms for. And then the motor themselves, you give them the same alarms. Okay, so you could have a 150 horsepower motor driving a fan and another one driving a chiller. They're drastically different alarm levels, but the motor has no identity anymore. So you do whatever this one's a chiller, you'd set your alarms at 0.25 and the motor driving it 0.25. Okay.
All right.
Statistically, it works out better that way. And then you're going to reset them with your own data as you go.
Okay, next one from Dennis. Motors seldom run right at rated RPM. Shouldn't all your frequency measurements be based on actual rotating speed versus rated?
Yes. The rated speed is on the nameplate, and it might be a few RPM off. It depends on what the final load is on the bearing or on the machine, the motor, what have you. Yeah, you should always use the actual RPM versus the rated RPM. If you're looking in a spectrum, you put your cursor on close to what the rated is, and you will get the actual.
Okay. So from William, why are the alarm profiles different on the same machine depending on whether measuring the motor versus measuring the shaft bearings carrying the fan?
Oh, why are they different? Oh, in that, right here. Okay, the reason they're different is in positions 3 and 4 on the fan also has a potential to have a blade pass frequency. Blade pass frequency is a pulsation from each blade going past, usually like in a pump, it's past the exit orifice and it pulses the liquid or the fluid. In a fan, it's going past some obstruction and you'll pulse the fan a little bit. The reason it's not in the motor is because there's no blades, there's no pump or fan in a motor. So these will show up on just the fans, the compressors, and the pumps in your system, and you want to trend that. So usually they're about 50% of the overall level is the allowable.
Okay. So for the paperclip example, the number of cycles affects the failure. However, the example does not mention the time taken to complete each cycle, or is that not a factor?
It is a factor in the metallurgy where your cycles to failure type thing, but it really doesn't depend how long it took. It would be a very short period of time for one of those three to fail if you were designing something like that. But in real life, it'll populate that slanted part of the curve, and you'll statistically get a curve that fits there. So I just did that to show you that it varies with frequency.
Okay. How do you deal with equipment being run on a VSD?
VFD, variable frequency drive. How do I feel about it? It's painful. Mm-hmm. The variable frequency drives will drive the motor or fan or what have you rated by the process. So if the process calls for a certain speed, it'll go to that speed. The problem with vibration analysis is the peak's constantly moving around. So the alarm levels, it might get into a different alarm level. They might get close to a natural frequency and amplify it. And, you might have certain conditions that you can't run just because there are problems when you run there, vibration problems. It just makes it a little harder. You're going to pick it up when you use these online transducers. So you'll probably have to have a secondary stream of information telling you what the frequency was on the drive and is basically what speed it's rotating at every time. Otherwise, it's a little hard. You'll get two trends out of it, or multiple trends out of it, I would think.
Okay. Is there ever a blade pass frequency for a TEFC motor which has an integrated cooling fan?
No, those cooling fans are plastic usually. There's two different types. The cooling fan in a squirrel cage motor or a cast motor, the rotor will have protruding fins on it, and as the rotor spins, it'll act as a fan, and that's what they're kind of designed to do. It's just an extension of the rotor bars, but they aren't really pulsing anything. They're just pushing air through. Your plastic fans on other motors, they're light and there's really no vibration. You know, they could fail and you wouldn't know it. You'd get an over temperature probably, but they really don't have a lot of impact on the vibration.
All right. And final question, this one looks like it's for me. Do you have a link for the YouTube recording? I've had a screaming 6-month-old on my lap for the majority of the presentation. Information upload has been a real challenge. Yes, so we will provide a link to this presentation. We'll get it uploaded to YouTube right after. We'll send that out. We'll send out a PDF of the presentation as well. And then we've also been getting a lot of questions about how our GraceSense predictive maintenance products kind of fit in with this topic. If you'd like to discuss the GraceSense products for your vibration sensing needs, please reach out to our sales team to set up a call. You can take the survey after and indicate that you're interested, or you can email sales@grace-eng.com, or you can reach out to me and I'll pass that along as well. I'm Nick Schultz. I've been emailing you guys about this. It's nschultz@grace-eng.com. So you should have my contact info. Hope you guys all enjoyed the webinar. Dan, thank you so much for coming back on. We're looking forward to closing this out on Tuesday. We will have more information about our vibration products in that webinar as well. So thank you.
Also, Nick, I do have about 60 questions that came from the first Tuesday seminar. You know, I'll try to answer all the questions and email them back out. Maybe put it into a PDF or something. So if you have questions, keep asking them. Be happy to answer them.
Right. So Dan's going to close it out on Tuesday. Again, questions about the GraceSense products, ship them our way. I'm not sure if we're going to be able to get to dive into our products very much on Tuesday. We want to get through Dan's presentation. But again, we'll follow up with anyone interested after the conclusion. So thank you everyone for coming, and have a great Thursday.